Welcome everyone to this month's TGRR seminar series. Before we start, we have a few announcements. The Transboundary Groundwater Resiliency Research, TGRR, Network of Networks is a project funded by the National Science Foundation's ExcelNet program to connect U.S. and international networks of hydrologists, social scientists, data scientists, and systems scientists to identify key data and system drivers that would make significant progress towards producing research that catalyzes transformative change for transboundary groundwater systems. And we would like to ask you to please join our Slack channel if you want to connect with more people and our mailing list. And we also have volunteer opportunities for early career researchers and students. And we would also like to invite you to our annual workshop, which is on September 28th and 29th. And we will have a systems mapping session to identify important variables and feedback loops. Now I'll hand it over to Christine Kay for Roslyn's introduction.
Thank you, Christine. It's all Christine's here this morning from TGRR. So I'd like to introduce our speaker this morning. Roslynn King is a PhD candidate with the Marine EM Lab at the Scripps Institution of Oceanography, which is also my home institution of UC San Diego. Her research focuses on the use and development of marine-controlled source electromagnetic tools toward mapping and characterizing a variety of resources of geologic or anthropogenic origin located on the continental shelf. And I would also like to thank her for being with us, as in 2 weeks, barring any calamity, she will be a freshly minted PhD and on to an illustrious career and protecting our important water sources. So without further ado, turn it over to you, Roslynn. And let me also say, you're welcome to put your questions in the chat and we'll take questions at the end.
Hi, everyone. I'm Roslynn King, as Christine just mentioned, and I'm going to be discussing some recent developments in marine controlled source electromagnetic technologies towards mapping submarine groundwater systems, progressing from known aquifers offshore New Jersey to some previously unidentified water sources offshore California. At the end, I'll leave you with a little food for thought on San Diego's offshore groundwater, and then hopefully we'll have some time for questions and discussion. So to get us started, I'd like to show you a cartoon of what offshore groundwater is, because it's not really a system that we typically think about. Here we have a simple cartoon depicting a generalized continental shelf. We have a bedrock layer overlain by continental shelf sediments, which are then mostly submerged with ocean water. We have simplified the continental shelf sediments as one group, but for the sake of this presentation and talking about groundwater, I'm going to highlight one confining rock unit, which is a very impermeable layer that can act to hold fluids such as water underground. And one way to introduce groundwater into this system is through modern meteoric recharge. So surface water fills up the continental shelf sediments, and if these sediments are continuous, water can make its way under the ocean floor and be held there via confining unit. If we start thinking about more ancient groundwater, water could also enter the system during glacial periods when the sea level is much lower than it is today, and the continental shelves are exposed to the air, enlarging the potential catchment area and allowing for fresh water to fill the pore spaces in the exposed shelf. This is known as paleometeoric recharge. At higher latitudes, and still with that same low sea level, water can be placed in the shelves through ice sheet melt. As the ice sheets melt, the melt at the base of and in front of the overlying sheets can permeate into the underlying geology, recharging the aquifer. And following these sea level low stands, when the sea level rises and drowns the landscape, bringing us to our modern sea level, the continental shelf is now submerged. And as the freshwater is less dense than seawater, the freshwater that is not confined will start to migrate upward and mix into the ocean. What freshwater remains below that confining unit may be left preserved in the shelf, either still in active recharge, still connected to that onshore portion, or isolated from the onshore hydrological systems. And this is the type of water I'll be discussing today, water contained within the continental shelves that are now covered by seawater. So it's important to accurately map offshore groundwater systems, as this knowledge can give us key insights into the paleo environment and water management strategies. If we study groundwater systems that had paleo recharge, we can tease out sea level changes, ice sheet dynamics, and other paleo environmental information relating to that groundwater system. If the groundwater systems are still hydrologically connected to the onshore groundwater, this could lead to saltwater freshwater interactions, and these systems could allow for saltwater encroachment through connecting geological features or units into the onshore aquifers. In these scenarios, the interactions between the onshore and offshore groundwater may limit the use of these systems for water management activities, such as aquifer storage, recharge, and recovery, or just simply extraction. And in essence, not understanding the character and size of groundwater systems that straddle the coastline can lead to inaccurate hydrologic models, which can be problematic for water resource planning. You can think of the issues simply as if you were about to go on a hike and you had a bottle of water, you'd probably want to know how much water it contained and if there was a hole in it. And lastly, mapping submarine groundwater can improve our understanding of global freshwater resources. And currently, submarine groundwater is not factored into resource budgets. But it could become a pretty important resource as countries become more and more water stressed over the next 20 years and beyond. So if we can improve our accuracy in mapping offshore groundwater and develop sustainable extraction practices, access to offshore groundwater resources could act to mitigate these future water stresses. So with that, I think we clearly have enough motivation to go out and map these offshore groundwater reservoirs. So let's move on to how these systems have been studied and how we are going to add to these efforts. So to get us started on the present knowledge of fresh to low salinity submarine groundwater, this figure shows locations where offshore groundwater have been observed or inferred. And you can quickly see that these observations have occurred on every continent. It's been estimated that 500,000 cubic kilometers of low salinity groundwater is stored in continental shelves. And to put that in more real terms, that's 22 times the volume of water contained in the Great Lakes. But this is a pretty crude estimate that is based on extrapolating data from just 7 locations, which I've noted with these yellow stars. Ultimately, we don't want to rely on these kinds of extrapolations. We would actually like to map these offshore groundwater systems, as each system may be complex or unique. Up until recently, exploration efforts have traditionally relied heavily on offshore drilling, which can be prohibitively expensive, oftentimes resulting in modest drilling programs. Drilling can provide a lot of information on the localized geology, and in some cases, accurately map groundwater systems, such as in the scenario shown here. In this cartoon, a freshwater lens, which is in blue, is preserved in the shelf and becomes progressively less fresh with distance from the present shoreline. This simplified groundwater system could be fairly well constrained with a modest drilling program. However, with modest drilling programs comes high levels of interpolation and extrapolation. And in regions that are geologically complex, such as the cartoon shown below, this can result in inaccurate depictions of the hydrogeologic system. Here, this region has been heavily faulted and contains localized features such as paleochannels that have been sized into the shelf, locally releasing the trapped fresh groundwater. In this case, drilling could easily underestimate the groundwater volume, miss key details such as hydraulic connectivity to onshore systems, or may miss the submarine groundwater altogether. In the case of complex and understudied regions, it's actually best to start exploring with remote sensing techniques. To remotely sense submarine groundwater in the case studies I'll be presenting today, controlled source electromagnetic methods were used. The systems presented were continuously towed, allowing for efficient and dense data collection over a region. These systems tow a dipole transmitter followed by some number of receivers. The transmitter generates an electromagnetic field, which induces a response from the Earth, and this response is dependent on the resistivity variations within the Earth. The resulting electric fields are then measured by the towed receivers. As controlled source EM is sensitive to changes in resistivity, this method is uniquely well suited to detecting fresh groundwater, which is significantly more resistive in comparison to seawater or the surrounding sediment. When we have processed the data collected using an EM system, we generate resistivity maps and profiles, which is indicated here as the modeled Earth property. I'll go into how we make these maps in a little bit, but for now, I'll discuss the resistivity and salinity. To characterize an aquifer, we must translate these resistivity models into salinity. To do this, we use Archie's law, which is graphically represented by this plot, where we relate bulk resistivity, our modeled Earth property, and salinity, our property of interest. Here I'm plotting salinity in grams per kilogram of water, and on the top I've printed typical water characterizations to give a better sense of what these salinities mean. So on the left we have fresh water, and on the right we have salty or briny water. Typical seawater is around 30,000 grams per kilogram and is within the saline water bounds. Archie's law depends on porosity, and typical sediments observed to contain freshwater have been found to have porosities that range between around 30 to 60%. In this plot, I am using the porosities of the freshwater-bearing San Diego Formation, which I will introduce later, and I have colored in resistivity values between these two end members. So when we go to interpret resistivity imaging in San Diego in terms of salinity, anything in between these two lines is fair game. In gray, I've noted two zones. The top zone is a resistive zone, and we can see that any resistivities noted with yellows or reds are representative of fresh or brackish water. And on the bottom, we have a conductive zone. This shows us that blue colors represent salty or even briny pore water. So to create these resistivity profiles shown in the prior slide, we must first collect the data. I'm preferential to the surface-towed CSEM system known as the porpoise system, as both efficient at mapping freshwater below the seafloor and can be used to survey large areas in modest amounts of time. This system is used in both of the American case studies presented today, whereas a bottom-towed system is used in the case study offshore New Zealand. Here on the left, we have a picture of the array waiting to be deployed from deck. You may note the GPS mast, which results in more reliable data collection with position, as well as accurate timing. The logger housing, which contains data loggers that record the GPS timing poles, pitch, roll, heading, position, and the inline electric field. And finally, the electrode spaced 2 meters horizontally apart on rigid arms. To the right, Chloe, who is an author of one of the case studies I'll be discussing today, and I are demonstrating the ease of deploying the system off the stern of a vessel. And as you can see, the system is lightweight, easy and quick to deploy, and tows upright in the water behind the vessel. Once deployed, the array tows behind the vessel in a line as shown here. The system array is made up of the horizontal electric dipole, which is noted with HED, that transmits a modified square wave, shown below, into the marine environment that is received by 4 receivers, labeled here as porpoises. Above is an example of a received signal. The receivers are spaced around 100 to 250 meters apart for a total array length between 400 to 1,000 meters, depending on how deep your target is. Behind the receivers, a dorsal brings up the rear and collects seawater conductivity, water depth, and temperature, which can later be used to build the models and reduce free parameters in our modeling software. During a porpoise survey, there is little to no real-time data to collect. In fact, if all goes well, it's usually a nice opportunity for a siesta, to catch up on some reading, chat with collaborators, have a snack. But once you get back to land and pop open the receiver housing, the real fun begins. When we download the data from the receivers, we will have navigational data and electromagnetic data. Each receiver collects 4 channels of data, which include the inline electric field data received on the electrodes mounted on those rigid arms. So that's shown in the top panel. Acceleration in 3 directions, which is not pictured, and a timing pulse from the GPS mast, which is noted in this bottom panel. The timing pulse is useful for correcting drift in the phase data, as it gives us a true time reference for accurate phase. It's important to remember that we are trying to determine what the electric field passed through to change the transmitted signal from this to this. And there are about 3 mechanisms that can result in a change in that transmitted field. Most intuitively, there is geometric spreading, which is where the amplitude of a transmitted field drops off with distance. So just the field weakens with distance from the source. Then the one that is most pertinent to today's discussion is galvanic change, which is an abrupt change in resistivity can cause abrupt changes in the electric field amplitude, which means that if we should see an increase in amplitude over a resistor, such as an aquifer. And finally, we have inductance, which is controlled by the skin depth equation that describes how a field decays with distance, with frequency, and in various resistive mediums. So essentially, the field will decay faster at higher frequencies and will propagate further in resistive mediums. So to determine the resistivity of the environment that the EM signal passed through, we must first process the data into a form that can be included in the inversion. To do this, we first pre-whiten and then transform the time series data into the frequency domain. The amplitude of the frequency domain data is plotted for all 4 receivers in the top panel. You can tell that we have some good signal, but it is a little bit noisy at this stage. You might also note that there are several high amplitude peaks, which may be indicative of resistors below the seafloor. This process reduces contamination from the Earth's field or the magnetotelluric signal and ocean noise on the data. We then post-darken and stack the data as shown in the middle panel. This process results in an error estimate and also helps to increase the signal to noise ratio of the data, which is shown in the bottom panel. At this stage, data with a low signal to noise ratio may be chosen to be excluded from the inversion code. From here, we can then build half-space models with varying resistivities that use some of the navigation data and run forward models to achieve predicted responses. The predicted responses to the models, which are plotted as these solid colored lines here, can be compared to the actual responses, those black dots, to test if the processing and assumptions we've done thus far lead to realistic results. So this is generally just a sanity check for us. Additionally, this plot is just for one frequency and one receiver. We can then take this process one step further and create pseudosections. Pseudosections are made by interpolating between the forward responses. So again, the same colored lines from the prior plot and the actual data from the survey to find the apparent resistivity of each point of stacked data, which will result in an apparent resistivity profile as shown here. These profiles can be a good indicator of lateral variability and resistivity of the subsea floor, but are not reliable at determining depth to the resistors. So to get a better idea of depth, we'll need to run some of those inversions. In these inversions, we want to determine the resistivity of the subsea floor. So we need to reduce as many free variables as possible so we do not create artifacts in the final resistivity model, and also to reduce sources of noise on the model. To begin with, we will include navigation from the survey, which I know I showed you an array towing straight behind the vessel, but often the arrays will crab through the water as shown, and we need to capture this behavior in the models. We also collect depth profiles both on the vessel and on that dorsal instrument at the rear. But again, real life is rarely simple. Instruments can ride on their sides or fail, resulting in bad or no depth data. And sometimes bathymetric irregularities just offline of the survey can cause misfit in the model, as we are a little sensitive to offline features. We can use publicly available data, such as this bathymetric map from NOAA of San Diego Bay, to parse out sources of noise and check our own bathymetric data. We also collect data of the ocean water, the conductivity of the ocean water at the surface, which can oftentimes be representative of the full water column in shallow water depth, but in some areas the water can be stratified, and the stratification must be included in the models. We can include these features by using data from our own CTD casts from the survey, or in some cases, we can use the publicly available conductivity profiles from the same survey day. I have had quite a bit of success using conductivity data collected by the nearby marine mammals on or right around our survey data days via the MEOP database. I really can't recommend this database enough. I love it. And finally, the seafloor often has layered geology, which can make it easier to pass an electrical current in the horizontal direction versus vertically through the seafloor, or vice versa. This is known as anisotropy, and it can be included in the models. In some cases, we may have an idea of the expected level of anisotropy from nearby drilling operations or geologic surveying conducted onshore. The models are built and run in MAR2DM, which is the publicly available goal-oriented adaptive inversion code from Kerry Key. We include all the properties I just mentioned and set them as fixed parameters, reducing the free variables to just the area below the seafloor. So that kind of lighter blue area in this figure. This region is then parameterized with a mesh that will coarsen with depth to mimic the loss of resolution with the EM method. However, the code will adaptively find the computation mesh if necessary. The inversion code will work to find the smoothest solution model that fits the data. This is known as Occam's inversion. So now that we've covered some of the basics of CSEM, I wanted to dive into a few interesting case studies where EM has been used to identify freshwater offshore. This map indicates known and inferred locations of fresh submarine groundwater. And the first use of CSEM to detect submarine groundwater is noted with a star and occurred offshore New Jersey. This region was chosen to test the viability of EM to map these systems, since the region was already noted to contain fresh submarine groundwater and had prior drilling campaigns and seismic data sets for comparison. And in essence, this first study is very pivotal as it built the groundwork for more CSEM surveys in other areas. So the first use of CSEM to map submarine groundwater was offshore the US Atlantic coast by Chloe Gustafson, who you saw earlier deploying some of those receivers. Part of the primary motivation for this study was simply to prove that marine EM methods were capable of mapping offshore groundwater. We, as EM geophysicists, knew that theoretically this would work very well, but we needed an example of this working in practice. And the area offshore New Jersey was the perfect place to prove this hypothesis, because there were several previously drilled boreholes that had already identified freshwater below the seafloor. And those boreholes are indicated in yellow as yellow dots on this map. So EM data was collected over some of these same boreholes, which is shown with the dashed white line, to hopefully demonstrate that there is good agreement between these in situ observations of freshwater and EM imaging. And the results were quite promising. Here is the resistivity model from that same survey line offshore New Jersey. On the y-axis, we have depth below sea level, and on the x-axis, we have distance from shore. The color bar shows log resistivity, and in this scenario, high resistivities noted in yellow indicate low salinity or fresh water, and low resistivities in blue indicate briny or salty water. This figure also has some seismic imaging, which we're not going to get into today, and the borehole locations are shown with a black dashed line. The dashed black line also represent a salinity of 15, which is about half the salinity of saltwater, seawater, and on top of these lines, the salinity of the pore fluids encountered in these boreholes is plotted in white. So anything to the left of the black line indicates low salinity, which should correspond with the yellow regions of high resistivity, and anything to the right of the black line represents high salinity water, which should correspond to our blue regions of low resistivity. From this study, we can see that there is overall good agreement between direct measurements and the resistivity model. I'm going to highlight 3 regions that have particularly good agreement. These first 2 regions, we can see that the upper and lower bounds of the aquifer correspond well with regions of persistent low salinity measurements. But we can also see good agreement between where the model has very low resistivities and the direct borehole measurements indicated the presence of brines, which is water that's saltier than seawater. So from the study, the authors demonstrated that EM methods can successfully map offshore groundwater, and not only that, they continued the survey north to identify a substantial volume of fresh water. So zooming back out to the map, the New Jersey survey is outlined in red, and another survey is mapped in blue offshore Martha's Vineyard, where there were no previous offshore boreholes. You can see that the results from this new survey look really similar to what was found in New Jersey. And even though there weren't offshore boreholes here, it's pretty safe to assume that this is another aquifer system, given what we know about the hydrogeology of this region. The authors propose that these two aquifer systems are likely part of a larger regional system that extends along the coastline, shown with this yellow hatching, and probably holds around 2,800 cubic kilometers of freshwater, which is similar to 1 billion Olympic swimming pools or 1.7 times the volume of Lake Ontario. Additionally, the trend in resistivity in the shoreward direction also suggests that there is a connection where water from onshore can make its way offshore and vice versa. And from a water resource perspective, this is a pretty double-edged sword. It both extends our water reserves, and which means that we could potentially pull that water from these aquifers from existing onshore wells. But it also adds another level of complexity because now, if while we're drawing that, we need to be really careful that we also don't draw in seawater into our existing aquifer. But all in all, this was a very successful first use of submarine groundwater. So returning back to the world map, the region offshore in New Zealand also shows signs of offshore groundwater from an IODP campaign that resulted in 2 boreholes offshore Canterbury. The freshwater encountered in one of these boreholes inspired Aaron McAuliffe and his collaborators to use CSEM to map the offshore extent of the aquifer. So hopping on down to the area offshore Canterbury, McAuliffe and others used a time domain CSEM system, so not the Porpoise system, to survey the areas marked with these red lines. From the prior drilling program, fresh groundwater was encountered in the U1353 hole, but not in the U1354. So it was inferred that the southern edge of the submarine groundwater lay somewhere between these 2 points. However, little was known as to the extent of the system here, to the right or to the east of these boreholes. So starting from the known, line 2, shown here, encountered some fresh to slightly saline water, those yellows and greens on this color scale, at depth, similar to what was found in the borehole, which appeared to become more saline with distance from the coast. These results are in good agreement with the previous studies and are similar to the scenario I presented earlier in this presentation, where a drilling campaign may capture the groundwater system effectively. However, the groundwater story is far more interesting to the east. On the right, we now have resistivity models from all 4 lines. And you might notice that lines 4 and 7 encountered stronger and larger resistors than in line 2. And these lines indicate there's quite a bit of fresh water than what was previously inferred from drilling. This is pretty exciting to see because this freshwater system was previously unknown. The 2 offshore boreholes from this region along line 2 indicated that there was some water that was slightly fresher than seawater, but there was no evidence for this large, fresher groundwater system that they had mapped using EM methods. This volume of freshwater in this system is around 56 to 213 cubic kilometers of water and has the potential to be an additional source of water to one of the driest regions in New Zealand. This study also included hydrologic modeling that showed some of this freshwater comes from onshore. So here we have an example of, again, another onshore-offshore connection, but most of the water that they mapped was actually in place during sea level low stands. So going back to that same inferred and known submarine groundwater map, you may have noticed that there are no indicators of offshore groundwater on the west coast of North America. So it might seem a little strange that I chose to work for look for these systems here in San Diego, but there was some evidence that fresh water was being drawn onshore from water wells. And as many of you know, water scarcity is a real and pressing issue in Southern California. So when I was devising a PhD project, this area naturally came to mind. And as a warning, this is my own project, so I will be spending quite a bit more time on this specific study area. So to get us started, it's best to describe what the current water resource situation is in San Diego. And to put it bluntly, freshwater resources in Southern California can be scarce and are probably going to become even more scarce. As such, the County of San Diego has recognized the need to plan well in advance the sources of its freshwater. Currently, San Diego purchases between 85 to 90% of its water from Northern California and the Colorado River, which is troubling considering the impact of climate change on these two sources of water. For example, snowpack in Northern California is expected to have a 48 to 65% loss by the end of the century. And the Colorado River is expected to see a 20% drop in flow by 2050, while demand on the river increases. As such, San Diego County has worked to decrease water use in the region, which has actually been really successful. They've managed a 30% drop in total demand, while the population grew by 35% since 1990. But the county is also looking into ways to diversify its sources of fresh water locally. So there is no one source or silver bullet to satisfy the county's needs. To meet demand, the county will need to make or recycle water, such as with the current Pure Water project, but will also need some natural sources of water. The San Diego Formation, which underlies much of the county, is the main source of fresh groundwater in San Diego, and the formation is currently being studied for potential aquifer storage, recharge, and recovery, or just increased extraction. Our study aimed to inform local water agencies of the offshore portion of this formation to make good decisions as to the management and potential use of this formation and resource. The San Diego Formation is within a structural basin, and the boundary of this basin is mapped in red here. This formation is very well studied onshore, but little is known of its character and pore fluid content offshore. As one can see in the figures here, and specifically figure C to C prime, a significant portion of the San Diego Formation, noted as TSD, extends past the present shoreline. Therefore, if we don't include this portion in our hydrological models, we may be overestimating the volume of water we are drawing from the onshore groundwater. And this inaccuracy could lead to problems with water management planning, such as determining the longevity of a well or desalination plant, inadvertent saltwater encroachment, or freshwater flushing. And this is a real issue, as we know we are currently drawing some of this water already from offshore. For example, using current recharge rates, onshore geology, and hydrological models, an estimate of the offshore contribution of water into the water monitoring wells is shown here in red. These results indicate that a significant portion of the water withdrawn from the San Diego Formation, or SDF, originates from groundwater under the Pacific Ocean. This groundwater volume is inferred, so we are essentially pumping blind. If we can constrain the boundary conditions of the San Diego Formation, we could better inform the water authorities of the storage volume of the SDF, potential freshwater flushing offshore or water loss offshore, or possible paths for saltwater encroachment. So that's what we sought out to do. So following a series of sensitivity tests and forward models to determine the frequencies and amperage that would yield the greatest sensitivity to the San Diego Formation, we set out to survey the San Diego Bight over the course of a year. As little was known of the offshore pore fluid character, we surveyed this region with 3 separate campaigns with enough time between deployments to process the data and identify resistive anomalies that may correspond to fresh to slightly saline pore fluids for further surveying. For today's talk, I will be presenting and discussing the results from the area within the dashed green box. And here are the vertical resistivity models from anisotropic inversions of the response data within that same green dashed box. Note that the black lines indicate recognized offshore quaternary faults, and the resistive profiles use a color scale where reds indicate higher resistivity and blues indicate lower resistivity. The first observation worth noting is that the depth of the resistors, yellows and reds, correspond to the depths in which the San Diego Formation is encountered in nearby onshore water monitoring wells, which is around 80 meters below sea level. Additionally, Dorigo et al., using acoustic reflection data and core data, interpreted the locations of these features to be the San Diego Formation. So we are interpreting the resistive anomalies to correspond to fresh to slightly saline groundwater within the San Diego Formation. This volume of freshwater is significant. It actually doubles the known groundwater volume for San Diego, with 103 to 154 previously unidentified billion gallons of fresh to slightly saline water. So what is probably first noticeable is that the submarine groundwater does not extend in a continuous lens from shore, such as in this cartoon, but instead appears to be in two north-south trending regions. Our proposed reason for this phenomenon is twofold: faults and paleochannels, which may have resulted in a situation similar to this cartoon block figure. This region is heavily faulted, and this is predominantly from the Rose Canyon fault zone. Here I have marked out the silver strand sections within this fault zone. This fault zone is within a trans-extensional regime and is made up of a series of dip-slip and strike-slip faults that have created down-drop blocks. These down-drop blocks, known as grabens, have created accommodation space for sediment as well as paths for ancient rivers, known as paleochannels, to flow. To illustrate the relationship between faults and paleochannels, I've enlarged a profile from our survey and overlaying Dorigo et al.'s geologic interpretations in white. The features labeled P in this section are paleochannels, and you might notice that these features are located on the downdrop side of many of the fault sections. Additionally, the TMP unit in Dorigo's interpretations refer to the San Diego Formation. And as you can see, the yellow and orange resistors are located within this unit, indicating freshened pore fluids. The resistors seem to follow the geologic contacts and are bounded by a series of faults. The faults appear to have segmented the submarine groundwater into several separate features, slowing or even prohibiting lateral freshwater flow across these faults within the San Diego Formation. If we focus back on the fence diagram, the freshened groundwater indeed appears to be fault controlled. This observation is consistent with the onshore characteristics of the formation, where the aquifer appears to be segmented into a series of separate groundwater systems, which have complicated efforts to model fluid flow and extract water from the San Diego Formation. The groundwater, discretized by those faults, appear to be disturbed by paleochannels. The paleochannel circled here in the upper left image appears to have incised into the confining units of the San Diego Formation, allowing for the freshwater within to mix with the seawater above once the ancient landscape was drowned with sea level change. This same paleochannel, marked EPC on the fence diagram, cuts through the survey, releasing the fresh groundwater below, separating the fresh groundwater on the west side of the survey from the eastern still connected fresh groundwater. If we focus on the groundwater further offshore, the resistive features indicated here are below what we in Dorigo et al. Have interpreted as a shallow paleochannel with saline pore fluids. However, unlike in the center of the survey, the freshwater remains sequestered in the shelf below this paleochannel. This is curious, but a possible explanation for this observation could be that the San Diego Formation has unconventional confining characteristics. So to elaborate, Wes Danskin at the USGS has noted that the San Diego Formation is lacking in a distinct confining layer or a trapping unit. But during drawdown tests at water monitoring sites, the formation responds like a confined aquifer. This may be due to a series of finding upward sequences within the formation that act as confining features. So this paleochannel may have disturbed some, but not all of these features. Here, it appears that some of the confining layers, for the most part, are intact. The pore fluids do not seem to be directly mixing with the seawater above. The paleochannel may not have incised as deeply into the formation, which also could have led to some preservation, disturbing these trapping layers because this paleochannel is within a graben, which is a downdrop section of geology caused by faulting. And this downdrop block may have created enough accommodation space on the paleo land surface for the paleochannel to flow, so the ancient river did not incise so deeply into the paleo surface. The offshore portion of the San Diego Formation, like the heavily faulted onshore portion, appears to be made up of a complex series of groundwater systems. The offshore section may be two discrete instances of submarine groundwater with an isolated western portion that is not connected to onshore systems and a hydrologically connected eastern section. The western section is most likely in place during sea level low stands and could potentially be used as a strategic resource but much more study is necessary to understand if this is possible. Additionally, from these results, we noted that the transextensional faults intersecting this feature may be enabling upward fluid flow or freshwater flushing from the submarine groundwater to the seafloor along the Silver Strand Section 1. This is not surprising, as historically freshwater flushing in the form of freshwater springs along this same fault zone have been observed just north of the survey area on Coronado Island. The eastern section appears to be connected to the onshore aquifer through a southern route near the Tijuana estuary. This feature highlights the complexity possible within a submarine groundwater system, which locally had been troubling hydrologists and geologists for some time. For several decades, some studies have indicated that when water is extracted from the San Diego Formation near the San Diego coast, the water became fresher and older as pumping continued. And we propose that the eastern submarine groundwater system may be the source of this old and fresh water. So I have often been asked what the offshore portion of groundwater means in the grand scheme of things for San Diego. So I figured I'd point out what San Diego water groups are currently doing and some possible uses of groundwater systems which have been done in other parts of the country. So the new offshore volume is between 103 and 154 billion gallons of fresh to slightly saline water, which sounds like a lot, but San Diego County uses 140 billion gallons of water each year. So this is not a life-changing volume of water for direct use. But it could be used for aquifer storage, recharge, and recovery, known as ASRR. The aquifer currently houses fresh water, which simplifies the process of using this formation for this purpose considerably. And using ASRR could play a key role in reducing our reliance on outside sources of water. Presently, we have the ability to scale our local water supplies to account for around 61% of our total demand using the means listed here. This would be an incredible boon for us, considering we're currently just using 10 to 15% local supplies, but it will be a massive effort to achieve. It would decrease the reliance on outside sources significantly, leaving San Diego far better prepared for expected water shortages in the coming decades. The county could attempt and is trying to look into being totally self-sufficient by also including aquifer storage, recharge, and recovery in its water management goals. The process of ASRR is illustrated in the bottom figure, where stormwater is captured and stored in groundwater systems during rainy seasons and then withdrawn from during dry seasons. This method has the added benefit of reducing loss to evaporation from reservoir storage, which can approach around 10% loss per year. So it's much nicer to store it underground. However, the pressing questions are, where do we get this amount of water? And then where do we store it? So surprisingly, San Diego County actually receives around 1 trillion gallons of water from rain every year, which is nearly identical to LA County, and most of this runs into the Pacific Ocean. LA has been experimenting with stormwater capture since 2004 with really promising results, and actually has decided to scale its stormwater capture plan to capture around 65 billion gallons of water by 2035. We could also attempt to do this here by capturing our own fresh water from the stormwater and putting it within the San Diego Formation. However, the issue might be complicated by the fact that the aquifer does straddle the US-Mexican border. But again, this is just some food for thought. I'd like to end by zooming out to our worldview of offshore groundwater and emphasize that the future of offshore exploration is wide open, and there is so much left to be discovered. The total global length of passive margins, which are these light blue fringes around the continents and where we expect to find offshore groundwater, is about 105,000 kilometers. So there's a lot more ocean to cover. Additionally, in today's examples, New Jersey and New Zealand are on passive margins, whereas California is not. So it was not initially identified on our map here. And more studies not shown on this map, such as in Malta, are being done with intriguing preliminary results. And I think this highlights that in addition to the sheer volume of offshore groundwater that We still need to explore. We also have a lot to learn about the different ways this water manifests in various geologic settings around the world. And I'm pretty excited to see what kinds of new groundwater systems we discover next. So thank you very much.
Thank you so much, Roslynn, and apologies for the Zoom that, it's not everyone clapping, the thunderous applause. Well, let me invite people to ask their questions. I have a few, if you have a few more minutes.
Oh, yeah.
Okay, so while people are formulating their questions, so I found it's fascinating. Oh, and we have a comment. John, thanks you for a great presentation. Thank you, John.
Thank you.
Let's see, so where to start? So could you say a little bit more about one of the last comments you made about how San Diego could recharge the San Diego Foundation, I believe you said it's called, but that would also, actions we take on this side of the border would also enlarge the water available for those in Mexico as well. Maybe you could expand on that a tiny bit.
Oh, yeah. So there are still questions out there about using the San Diego Formation for aquifer storage, recharge, and recovery. Specifically, when I showed that map of the basin, it's not well constrained south of the border. That's an approximate boundary based on like a slope. It could go farther into Mexico, and there's a lot of faults out there. Additionally, those faults in the San Diego Bay, for the most part, are pulled apart, so allowing freshwater flushing in some areas, but are sometimes a little under compression as well. And we don't really know what would be happening in that region offshore the Mexico border. So you could potentially pump your own water down, the storm water, and then it may just leak offshore. So you would want to do more surveying south of the border before you go ahead and start using it as a bucket, because there might be a hole in your bucket. So
I'm glad I asked.
Yeah.
So I know in other conversations we've had, and stop me if this is nothing you want to say on a recorded Zoom, that you were unable to map the whole submarine aquifer because it encroaches on the Mexican border. So I wanted to ask you, what would be your policy wish list? And do you know of any other places in the world where countries collaborate on mapping submarine aquifers?
Ooh, I haven't heard of any countries that are collaborating yet. The UN has listed controlled source EM as like the main method to find submarine groundwater in a recent report. So I'm assuming that there will be more efforts worldwide to actually start to map these systems as they cross over borders. We are working currently with, we're trying to get something off the ground to actually start mapping south of the border. Nothing yet, but we'll see. There's a lot of permitting issues and things like that, but we'll see.
So is it where you need the federal government to work with the other federal government, or is it municipalities that sometimes, or maybe you don't know because you're still trying?
I'm not sure. I think for us to map it, there's not that many hurdles to get through. Well, that's kind of naive to say, but I think there's not too many hurdles for us to map it. But I think if you did start using it as a resource, there may be some like a handshake that would have to happen across the border between federal agencies.
Sure. So on the subject of policy, in studying this, do you have any worries about the potential exploitation of these kind of resources?
Oh, I'm very worried about exploiting these resources. The issue is that currently we are exploiting them. We just didn't even know we were. So for Chloe's study area offshore New Jersey, those systems are fully connected, and they've been drawing water from them for a long time. So who knows how far out that lens used to be, and now it may be closer to shore, or maybe it's actually recharging really nicely. But we don't know. That's the issue. And in San Diego, we knew we were drawing water from this system. We just didn't know where it was or how much. LA was running into the same problem. They've been drawing from their aquifer for a long time, and now they're actually using a pressurized, they pump down to actually keep like a pressure barrier against saltwater encroachment. Ventura and Oxnard are a story of caution, those two areas, because one, they both have the same aquifer, and one has managed to protect it, and the other one has drawn saltwater fully onshore. And once the saltwater is in your aquifer, there's not really any going back. So I do want people to not see these aquifers and be like, yeah, this is the future. Let's start using it right now, because we really don't know how much they're recharging. And these systems are really complicated. We might not even have the resolution with the CSEM method to really see if there are like holes that we're maybe having flushing in small areas. We might miss that with the method. So I really do want to like have a word of caution before we start using them.
Yeah, I think in our lifetimes we might see fresh water supplant oil as a scarce resource, and for cost. Perhaps it already is more expensive in some areas. And please, if anyone has questions, you can jump in. Roslynn knows I have like 1 million questions for her always. CT, please.
Yeah, I just have some operational questions, and I apologize if you already talked about this. It was a lot to take in because I don't have a water background. But how often do you go out and survey the same place, and do you do it after each earthquake?
Oh, that hasn't been done yet. We did this survey, the one in San Diego, over 3 different campaigns, but we didn't run any of the exact same lines. The one thing that was kind of, I don't know, showed some stability in the features is that when we have tie lines, they appear to be consistent. And so it didn't appear like the aquifer was changing those shapes or anything. But in the other 2 certain areas that I presented, that was done in a single survey. It would be really interesting to continuously monitor, and there is some talk of doing that in some areas where you could actually deploy a series of MT, so not controlled source EM, but a passive system, and put them on the seafloor and just have them connected and maybe talk to them frequently and see if things are changing, or just resurveying the area, because it might be cheaper to just resurvey. The system that I showed, the Porpoise system on the boats we use, costs about $2,300 a day to survey, and we collect like 30 kilometers of data. So we can do quite a bit of surveying and not much money, especially compared to a well, which may cost $30,000 to $40,000 to put in conservatively.
Right, or a long cruise, or
yeah, exactly.
So I was really intrigued by what you said about freshwater flushing in the ocean. And I was just wondering if that creates unique marine habitats, or if there are people that study that.
Yes, people do study that. I don't know very much. This is outside of like what I know, but I know that freshwater flushing, freshwater springs offshore do create kind of specialized benthic habitats. I think there's a famous example. I don't want to say it because I'm not sure. Look into this, grain of salt. There's the corals, they're deep water corals in the Gulf of Mexico, and I believe they're the result of freshwater springs. But please read into that first.
Well, and I know this is far outside of what we invited you to talk about, but since I don't have anyone else to ask, I mean, I can't even imagine asking this question. So thank you for taking all my 1 million questions. And
we are looking for freshwater springs for archaeological reasons, because we believe the first peoples in America would have been drawn to the freshwater springs, as well as paleo channels. So we do use EM to map freshwater springs from an archaeological perspective. If that's a animal, you said, living things.
Oh, so interesting. Well, my last question that I'll close with is a little silly. The American Geophysical Union, which for those of you who are on the others, maybe we have people here who are systems scientists. It's our place that the geoscientists meet. They have a contest this year called Quilt Your Science, which you're also allowed to knit, crochet, I think mixed media or anything. But if one were going to quilt a submarine aquifer, do you have any that you think are particularly beautiful?
Oh, I'm partial to my own in San Diego because I really love how it's all separated. But even just I know Chloe's study, it looks a lot like a duck, which would be kind of fun.
Oh, okay. Okay. Well, I'm going to check back in with both you and Chloe and show you my handiwork. We have until November or so because our annual meeting's in December, as you know.
Yes, awesome.
Well, with that, I'm going to close this webinar. I'm going to thank Roslynn, and I know in 2 weeks, Dr. King. So we're very excited for you. I think you're all set. Thank you for the work that you're doing. My kids and grandkids, thank you, especially as I'm guessing it will be part of the the water plan here in San Diego generations to come. And yeah, thank you to the community too for being here and people who watch this later on the recording.
Thank you so much, everyone. This has been fun.